So let's look at problem 11.8 from the book, and we will use this problem as an example to describe the typical procedure used to solve a problem with the principle of virtual work. So the problem is showing us this bar supported by the spring and a smooth collar that allows the spring to be always perpendicular to the bar for any angle theta. That's an important information. The spring is always perpendicular to the bar. If the unstretched length of the spring is L0, determine the force P needed to hold the bar in an equilibrium position theta. So we need to find at what angle theta the system is in equilibrium. Neglect the weight of the bar. So the procedure for virtual work is we start the same way we do for any static problem, so by drawing the free body diagram. So we draw here just a bar, the angle theta. So then we have the reaction forces in A, which are two forces, one along Y and one along X. Then we have our spring force Fs, where this projection here is equal to A, as indicated in the problem. And then we have our force P at the other extreme. Now, after we draw the free body diagram, the next step in a virtual work problem is to draw the deflected position. So we need to choose what type of movement we are going to give to our system, what virtual displacement we will be using. Here the problem itself is suggesting us what's the most convenient choice, and it is rotation, theta rotation. So the displaced position is going to be this, and the displacement is going to be delta theta. Then I'm going to relate the displacement of any other point to delta theta. So I'm going to have delta S, I'm gonna call it, is the displacement of the spring. And then I'm gonna have a certain delta Y here, which is the displacement at P. The next step will be to write the virtual work equations and to solve, to express all the displacement in the virtual work equation as a function of the displacement variables I have described, and then to solve this equation. So let's look at these steps. I'm going to make some room here in order to be able to solve the equations. Okay. First thing first, let's write the spring force. So S, which is the position of the spring here. Now, if you remember, the force of a spring is K times the displacement that the spring undergoes with respect to its its original position. So the force of the spring will be K times S minus L0, where L0 is the resting position of the spring. S, I know A is given from the problem. S is equal to A sine of theta, as I can see from the geometry of the problem. So in this way I've written the spring force, and when I'm going to write the virtual work equation, that's gonna be du delta u is equal to minus fs delta s. Why is minus? Because the force, the spring force, is going to be always against the, not always actually, is going to be against the displacement of the spring itself. If I look at the displacement diagram that I've shown in red, the force is going against the displacement, right? So that's a negative sign because those are two vectors those are two vectors with opposite directions. P instead goes in the same way of the displacement. If the displacement was dy and was going down, so delta y, so P is going to be P times delta y, and this is equal to 0. So in order to solve this equation, now the next step, and the critical step, is to express delta s and delta y as a function of delta theta of my displacement. And this is where comes to choosing the most convenient displacement. So you can write the virtual work with respect to any displacement, but then you have to manipulate this function in order to have the virtual displacement has to be the same. In this way you can simplify it. We can do this in several ways. So let's look first at the spring. We want to write delta s as a function of delta theta. There is the geometrical way of doing it. So if I look at my delta s is this. So this length is equal to this element, this section here of my beam, times the angle delta theta. So I need to find what this section here is. That section here is A cosine of theta, right? For a very small movement, this is what it is. So my delta S is going to be equal to A cosine of theta delta theta. Now this approach works in this case because it's a very simple geometrical problem. In general, it's much better to use an analytical approach, a mathematical approach. What is it? So delta S, I want to write delta S as a function of delta theta. So I basically want to do a derivative of S with respect to theta. So I write my function S as a function of theta, and that's what I did here. S, this section here, is equal to a sine of theta. So I wrote s as a function of theta, and now I derive this function here with respect to theta. So I get a, because a is a constant, the derivative of sine is cosine, so a cosine of theta. So now I have delta s over delta theta is equal to a cosine of theta, which is basically the exact same thing I got from the geometrical consideration. So now the next step is to express delta y as a function of delta theta. So let me make some room. I will keep the virtual work equation because it's the virtual work principle is the most important part. It's the one that you always have to keep in mind, and you always have to write it down. Now I want to express delta y as a function of delta theta, so let's do directly the geometrical approach. What is y? So the y location of my point P here is this location. I'm gonna use orange, so you should see it. Is this location, is this coordinate here? And that coordinate, so y, is equal to the length of my beam sine of theta. You should agree with that. I do the exact same thing as I did before. I want to express delta y as a function of delta theta, so I derive my function y with respect to theta. So I get delta y delta theta is equal to this derivative. So the derivative L is a constant, it stays there. The derivative of sine of theta is cosine of theta. So this is delta y over delta theta, and then of course delta y is equal to L cos theta delta theta. So now that I have expressed both delta y and delta s as a function of delta theta, I can rewrite my virtual work equation, which is going to be so that equation is going to be minus fs, which is k s minus L0, and L0 is a sine of theta, minus L0 times delta s, which, if you remember what I did before, it was a cos theta delta theta. Then I have plus p, my load p, L cos theta delta theta, and this is all equal to 0. So I can simplify delta theta everywhere. I can actually also simplify cos theta everywhere. Sorry, there was a theta there. And I end up with equation to find p, which is p equal k a times a sine theta minus L0 divided by L. So in this way I solved the problem.